G'day everybody and welcome back to the channel. Now, don't freak out, it's all good. I have not gone and built this off of camera. I'm just re-recording the intro to this video. So before everyone looks at this and goes, what the hell, why didn't we get to watch? Don't worry, that's coming up. The reason I re-recorded the intro is because I noted down all these random component values and started talking about them in the intro, and well, let's face it, this only makes sense to people who design stuff and even know what I'm on about. I mean, I'm using my own abbreviations here and everything. So I thought that was a silly idea. So I just scrapped that part, which was in the original intro, and I've just started building the circuit and just videoed that, and that's it. I don't know how to sum that up better. Basically, I just saved a lot of time that was unnecessary in the video that would have just confused a lot of people, basically, is what I'm trying to say. Just a small disclaimer before we get on with the video. I had to go back and open the back of this because the idiots that made this had run the collectors straight off the bridge rectifier, and then get this, run a wire out from the bridge rectifier to the capacitor. Who does that? So I've made a wire split in there with some heat shrink and 2 bits of this wire that goes to the 2 collectors. That's the collector wire coming back out, and then the positive off the bridge rectifier is coming straight out as a positive. I've also put 2 1K resistors in here, base to emitter, on the 2 series pass devices. Just wanted to point that out because I didn't film that bit. I started doing it, and then I said I'm not going to film this. The back's been off it that many times. I don't want to make people just keep watching the same thing because I forgot to do something. So I mean, yeah. Alright, on with the video. Alright, so I've set up all I'm going to do off camera because I want to do everything off camera. This is a different style of video that I'm doing on this one. This is sort of like an engineering blog sort of thing. So you're going to get to see the entire process from, as we saw in the start video, just taking general measurements and stuff like that, to talking about what we're going to do, looking at data sheets. I mean, I only need 2 data sheets and a calculator to do this whole job, but anyway. And a multimeter and a scope, obviously. But yeah, so these videos are going to be longer, but if you're interested in watching someone design something or you're trying to learn electronics, this will be for you, because you'll get to see this from beginning to end, unlike some of my other videos where, like for instance, where I've started my YouTube channel in the last 3 months, half the power supply, the big one I'm designing, was already built, so you guys have missed out on that. This you get to see from the start and all the working out. Also, we'll draw a schematic of this. So every time we finish a video or a bit of circuitry or whatever, there'll be a schematic for it, either at the end of that video or at the start of the next video, if that makes sense. So this whole series will contain everything that you need to know. Anyway, we've got our main bulk cap here for our main rail, and we've got our collector going back. We've got our output over here. We've got our MJE2955 here with its emitter going back to the the bases of the what do you call them? Series pass element. God, going silly for a minute. Where have my tweezers gone? Okay. So what we've got on the main cap, if you look at the meter, we've got 24.89 volts, and on the second cap, 24.87. Alright, so first thing we're going to do, I think what I might do is I might just scatter these components here too, because it's actually easier for me to see. I don't need many components on the table, many different values to play around with for this particular thing that I'm building, so I might as well just put everything on the table. It's not like it's gonna be too much. It'll be a lot easier for me. Just sort of spread everything out so I can see what's there. Yeah, that's good. Okay, so first thing I'm going to do is I'm going to grab a 1K resistor. There it is. Pin 1 is the base, pin 3 is the emitter, pin 2 is the collector. Okay. We're going to put this 1K resistor from base to emitter on this 2955 transistor. That can't be a 1K, that's got a bloody red band on it. Sometimes these resistors are just stupid. That's 1K. Look at this. You can see the difference between the brown and the red, surely. Even though it's hard to see, you can see it, right? That's crazy. That's the only thing I've noticed over the years with J-Cars resistors is that the markings on them aren't too clear sometimes, but the quality of them in terms of tolerance and power handling, they're half watt metal film resistors, and they actually are. So that's great. Alright, we're going to put a 1K resistor, just one end of it's just sitting in the base pin. Get it in there. In the base pin of that transistor. I'm just going to pause the video and grab some link wire. Actually, for the sake of this, because I'm trying to do this on camera and I want to make it easy, I'm just going to use these crappy things. I've had really bad experience with them. I've got a whole bag of them. I've got male to females and everything. We'll just use these for this. It'll do the job. They're not ideal by any means, but they'll work. Well, we're going to put one wire in the collector. We're going to take the other end of that wire and we're going to bring it back over here and put it in the positive side. Right? Okay, now we need our 2 547s. I'm just going to splay the pins out just a little bit so they fit in the breadboard. Now with these, it goes collector, base, emitter. I'm just going to have a look at the data sheet to make 100% certain that I've got that right, but I'm pretty sure I've got that right. Collector, base, emitter. Yep, that's the one. Just like the 550s and all the rest of that series. Alright, so what we're going to do is we're going to put one here. Actually, I'll actually put it over here a little bit. Let's see why soon. And the other end of this 1K is going to go to the emitter of this BC549. Sorry, 547. BC547. Let me point one thing out. If anyone's trying to build this at home, you need your transistors on a big enough heatsink and a big enough transformer to accomplish what I'm going to accomplish. All the rest of the component values, yeah, you can copy them, but that'll be a caveat. Even I don't know how much constant power, continuous power I'm going to be able to get out of this heatsink and this transformer. I don't think it's going to be much. So we'll have to see as we go along what we can get out of this. But anyway, just want to point that out. So I'm just trying to think how I want to do this. What I'm going to do is the base pin of this transistor, I'm just going to bring out a little bit further I'm just going to move these other 2 pins over a little bit like that. It's not perfect, but it will do. That way I can put the emitter straight in the base of that transistor. But I still have the other 2 pins in 3 open tracks. Now, we want to connect the 2 collectors together. I'll see if I've got a small little link. Yes, that's not oxidized. That's the thing about jumper wire that you make yourself. The copper gets oxidized over time, especially if you touch it with your fingers, and you have to re-strip it. And it slowly gets shorter and shorter and shorter. So we're going to connect the 2 collectors straight together. Like so. We're going to also, now in the real build on the circuit board, it won't be laid out exactly like this, but well, it probably will be. I'll probably have a thick trace going over to the driver and this coming off of that, but the trace will be a lot thicker than this wire. This isn't ideal, having wires this thin and then daisy chaining certain things off of them, but it will do for what we're trying to accomplish here. So now our collectors we're going to give power to. We've got all our collectors connected together now on our triple Darlington. Sorry, it's a quad Darlington because this is driving 2 transistors that are essentially in parallel, so it's quad Darlington. Now we're going to take a 4.7 kilo ohm resistor. We're going to put it base to emitter on our second transistor. Not the first one, just the second one. Like so. Right. Now we're going to take our BC550 and we're just going to put it about here. Now we're going to take the we're going to take this there it is. You call it 222. I'm going silly for a minute. 220. Wait, no, 2,200 picofarad. No, 220 pico. I think it's 220 picofarad. I'm literally just putting this on my LCR meter because I've literally forgotten how to count. Stupidest things happen. Sorry, it's 2.2 nanofarads. The things I do sometimes. I was trying to say 2.2 and I don't know why my brain was trying to go somewhere else. That's going to go between the collector and the base of this transistor that's going to be our comparator. Again, that's going to be hard to get in the holes. we want, am I missing a 1K resistor? One moment. Alright, 1K resistor is procured. We want to put this guy in the emitter. Sorry, not the emitter. What am I saying? On the collector of our comparator transistor. How do you get in there? Alright. We want to get this into the base of here, but we don't want it to short out on the collector. Oh, you know what? We can sneak it in from behind like this. Perfect. Not a worry in the world. There we go. The only worry is trying to get it in the hole. I got it in there. Yeah. No, that's bottomed out and it just fits. Cool. Can't complain. Alright. Let's see, what do we got? Alright, so now we want to take our 22K resistor. That's going to go from this second stage filter, from the positive here. That's going to come over, and that's also going to go into the collector of this comparator transistor. I'm trying to keep this fairly neat so that people can see what's going on if you're wondering. I'm not normally this fussed about making my breadboards neat. And honestly, I've seen people that do a lot neater work than this. I'm not saying this is neat. I'm just trying to make it neat enough. Anyway, I digress. Now, what we want to do is we want to take our emitter and bring it, let me get some more appropriately coloured wires out the bag. A few different lengths, that'll help. For those wondering, yes, I know this is powered up. I'm too lazy to turn it off. If I get to the point I feel like I'm going to short something out or pop a transistor, you know, by shorting something out, I'll turn it off. And it really doesn't faze me. You'll be surprised. I'm a little bit crazy like that. I wouldn't say it's craziness. I've just been doing this for a long time, so I'm just comfortable with things that are switched on. I'm not recommending anyone gets in the habit of it, because unless you are really experienced, and even if you are, you can still have mistakes. You don't want to get electrocuted. I mean, you can't get electrocuted off this. It's only 24 volts. So this is going in the emitter. This is coming over to here. Shall I put it there? And we're also going to take another wire from the start of our first capacitor. We're going to put it right there. Just give these a bit of a slide up and down to make sure that any oxidation's scraped off. Right. I'm just trying to think how to utilize the space I have. Oh yeah, I'm gonna crop the leads on this. Also, we want this capacitor. We shouldn't have anything on the output at the moment, but I'll just make sure. Okay. Oh, yeah, we should. I haven't. There's nothing to pull it down. One moment. Now there's nothing on the output. Wait, what? What have I done? Hold on a minute. Collector, emitter base to emitter to base, collector. What? Hold on a minute. That's not right. What have I done? I've got something wrong here and I've got to work out what I've done. This is the base drive wire, isn't it? Oh. What have I done wrong? That's the emitter. Yellow is the base. Well, these transistors just got charged on the base and they're turned on a little bit and there's not really any current there, or is something up is what I'm wondering. Let's do something else. That's always a good idea when doing this sort of work, and change over to some different leads. Right, if I take this base, wait, what? Okay, something is really odd here. I'm gonna have to have a quick look over this and see what I'm missing. I'll pause the video and I'll be back in a moment. Well, I'm a freaking dummy. We're gonna have to make some slight modifications. Everything here is correct. In fact, even this wire can go back in this hole. This can go in here. There's nothing wrong there. The series pass elements are PNP devices, and this is a PNP device. I am building an NPN circuit. So it looks like those CDIL 3055s are going in the back of this now. And this is going to get changed to, I don't know, probably a tip 41C. Yeah, tip 41C will do the job. I've got plenty of them lying around, I'm pretty sure. Oh well. I wanted to keep all the original parts, but I really don't like PNP series pass based power supplies. I've got my reasons, but yeah. So, and I've also just wired everything up for NPNs. before I load these transistors and damage them, let's get them out and swap them, because nothing needs to be changed there or here. We just need to pull them out, put the new ones in and swap that. I'll do this off video. I'll come back when it's done. If anyone's wondering, I've been using it. Very happy. I hope this doesn't come to bite me in the arse, but I've just realised I also need to get a data sheet up for the 2N3055s, because I don't know the pin out for that off by hand, and well, knowing my luck, the sockets are wired up wrong. Please don't be wrong. Please don't be wrong. God. Two in 3055. Bloody hell, the pinout's not in the data sheet. What the hell? Oh, it's down here. Okay. Looking at it from the bottom, pin 1 is base, pin 2 is emitter. You know what? I think that's how it was wired up. I am 99% certain of it. So I'm going to fit these. I'll just pause the video. Sorry, my apologies. It's getting stuck fitting a transistor. Alright, so I've got the tip 41C here too. Let's make sure that's off. We'll mount it to the little heatsink block when we go to put it on the case. And I've got the CDIL 2N3055s on here. Alright, now with those changes, we'll power it up again. Need more space so that I can get this on camera for you guys better. That's better. Cool. Alright. Power it up. Now there should be power right now. That's better. And when I take this out, it should go. Okay, we still have issues. That's not good. What? Do I have these sockets wired up wrong? Oh, it's going to be my luck, eh? It's going to be my luck. Let's see. I'm just going to see if I can look in the back. Yeah, I can see. So, emitter on the right. Oh, I just realised something. That's funny. Oh, that's real funny. Okay, we need to take the back off. That's embarrassing. Wow. I'll leave a comment in the first video so people don't get worried. I even before, oh, this is annoying now. Before I even realised the transistors were wrong and swapped them to NPNs, my base to emitter resistor is going between the bloody collector and what looks to be the emitter. It's not between the base to emitter junction, so I'll go rectify that off camera too. Oh goodness, no wonder the thing's still stuck on. I'm gonna have to clear myself some space. Good thing for me, I have all these wires made up to just pop out the board. Otherwise, that would be a bit harder to do. Alright, I'll show you what I've done. I've put my resistors going from, this is the collector. Collector to base. Sorry. Oh my god, I've gone collector to base on this side and collector to emitter on this side. At least one end of the resistor was in the right spot on each side. God. I'm not going to lie, I'm just going to do the bodgiest possible thing and just heat it up, get as much leg as I can sort of pry out. Actually, there's a bit there. If I can get the cutter in there somehow. Yes, I can. Through here. Well, that's embarrassing. I won't lie, I am kind of rushing a little bit. Not rushing, just I'm not putting too much effort into it because it's just such a simple build. And well, yeah, I've kind of screwed up there, haven't I? Not to worry, it's easily fixable. At least I don't have to rewire the sockets. The base, yeah, the base is on the left and the emitter's on the right, so that's good. Alright, that's one. What can we do for this one? That's enough anyway. If I can just fit this in here. Give me my resistor. I want my resistor back. Thief. I got it. That's good enough. Good enough for Australia. Get over it. Good. Alright, I'm going to solder those two resistors in place. Can't believe I did that. Alright, well that's that problem sorted out. I just cannot believe I did that. I feel like a bloody fool right now. I'll tell you, honestly, of all the things I could have done, I put a bloody resistor biasing the transistors on. And it's a 1K resistor that can supply a little bit of current. I mean, it doesn't have a driver, so it's limited, but it's still a bit. That's funny. Oh well. I'll just pause the video whilst I set this up for your sake. Sorry. Okay, let's try this again. Power on. We should have power now. Ah, that is looking correct. And now we should have nothing. Yep. Now it's working. What I was thinking before, I don't know. Anyway, moving on. So let's continue building our circuit. Now that that little incident is dealt with, I still can't believe I did that. I'm going to turn this off. What we're going to do now, we need our Zener, our pot, we need to create a feedback network, and we need our load resistor. Now the pins on this are actually even thicker than my tinned copper wire. I don't want to make the slots on the breadboard too wide. I've already buggered a couple. So I'm just going to solder a couple little bits of tinned copper wire onto the legs of this resistor. Just so we can make it longer. I need to wet my soldering sponge. Actually, I need to go give it a good wash. Alright. Our resistor. Whoa. Come back. Just threw a roll of tinned copper wire everywhere almost. Alright. Let's put our load resistor in. It'll go just like that. And this is going to be our, sorry, that's supposed to be my output capacitor. I don't know why I put that there. My bad. The 100 microfarad cap that goes here. For those wondering, I am literally just doing this as we go. I'm making this up, you know. That's why I'm saying this is a different style of video I'm trying here. It's, like I said, it's more of an engineering blog. So there we go, that's our output capacitor and our load resistor. Now off of that we need feedback. So I need to clear some space. We don't need to worry about this diode for now in breadboarding this because, well, this is going to go across the output terminals for one, and it's only to stop a spike coming back in the terminals from an external circuit, which we don't have at the moment, so that's perfectly fine. Omitted. These components are here because we'll need to do compensation and snubbing things, and these also we don't need right now because that'll be a common mode network for the output. So that's all I need on the table really. Now I need to know which end of this wiper, so which end of this, oh no I don't, what am I saying? I can work that out afterwards. One end of this needs to go into the positive from the output. Dude. Right. Alright, I've just been doing a little bit of work off in the background. I was just getting up to the part where I've got to add a Xena to it, or maybe two Xenas, one as a reference and one to cap the maximum voltage. And I started doing a load test, which is what I've got here on the table, going to the load bank, and that's set at 1 amp. Oh man, that is so annoying. How can I make that go grey? I can't. Anyway, you have to take my word for it. It's turned on. It's set to 1 amp. Now, I've got the load directly attached to the wire coming off the emitter, and the other end I'm putting straight back to the negative wire here, so there's no volt drop across wires. And we're losing about half a volt. I had to actually go over the circuit because this circuit's got a bit of gain. There's no reference or anything in it yet. The regulation can be improved a little bit, but still that's quite poor. That's only at 1 amp. So I end up taking my multimeter and putting it on this end. And I can tell you now, this is not going to be anywhere near what I thought I was going to get out of it, but at the same time, it's not really the end of the world. I can get a bit of power out of it just further down in voltage. So it's a two-part reason. Partly it's because I'm making it NPN, so there's 4 VBE drops. So that's, I don't know, what, 6, 12, 7, 14, 3, 2, maybe 3.5 volts that you're wasting, maybe even more. 3.5 to 4.5 volts, depending on the volt drop on the transistors under load. Probably 3.5 volts, somewhere around there, I'd say. Anyway, subtract that from what's left on the rail once it's loaded, and it's not much. I'll just show you. Oh, well, at 3 amps, $16 volts it drops down to on the output. And just to prove that it's not my regulator circuit oscillating or not regulating, I'll show you what's happening on the input. It's the power transformer. 24 volts, loaded at 3 amps. We've only got 21. So take off another, say, 4 volts, let's just make it easy. That leaves 17 volts. And you see the problem I'm having. So there's no way of getting 18 volts at anything more than an amp. With reference diodes, shorter wires and thicker wires, and a PCB and all that sort of stuff, better regulation, it'll be able to do 18 volts at 1 amp. It'll be able to do, say, 16 volts at 2 amps. I've tested this already off camera, so when you get down to about 13 volts, it can start to supply 4 or 5 amps. The thing I don't understand is on the bottom of it, it says 8 amps. And if I load 8 amps on it, there's way less than 13 volts here. So I don't understand how this thing was ever, unless they're doing some voltage doubling thing with the rectifier, because it actually did seem like that. But anyway, we want a nice smooth supply, so I'm not bothered by that. What I'm going to do is I'm going to put a Xena in the feedback path. How do I explain this? sort of across the wiper going to ground via a resistor. That'll cap the output voltage so it can't get turned up above 18. And I'm going to put another Zener, I think, in the emitter path of the comparator transistor, and I might give it a little bit more current too. That resistor might get changed to 10k or something like that. I don't know. We'll see. So the Zener's got enough current to have good regulation. And then we'll see what sort of performance we can get out the circuit then. But like I said, this is only going to be a simple circuit, so 2 Zeners is already pushing it. I still haven't decided whether I want to add fold back current limiting or not. The thing is, there's only enough room in the case to put 1 panel meter. Actually, yeah, no. There's only enough room to put 1 panel meter. The 3 banana jacks, power switch, LED, panel meter, and voltage knob is just barely going to fit. So I don't think I'm going to get any current control circuitry in this one. But that's alright, it is what it is. Can only fit so much in a little box. But yeah, it's going to be able to, I mean, at least it's more useful than what it was. It only went up to 13.8 volts. It was fixed. Now I'll be able to get more voltage out of it at the sacrifice of current, or I can come back down in voltage and get more current, or I can go down even lower in voltage. I can't get even more current. Maybe the transformer could dish it out, but the transistors would heat up that little heatsink quite fast, trying to drop almost the whole voltage that the transformer's supplying. You get what I'm saying? Although it sags quite a bit. We can't really answer all these questions until we finish building it, but I can tell you now, in the first video I thought I was going to get a lot more out of it, and I can tell you now we're not going to get that much out of it, but it's still going to be a very useful supply for single-ended preamps and a lot of different circuits that I build. Look, my goal for a while has been to get a few power supplies going in here, so that sometimes I work on odd things that have multiple rails, and that's why. So it's going to be helpful no matter what. It's not going to go to waste. It was going to waste sitting on the shelf how it was for the last couple of years, just stock. So like I said, I've got a few things to do, and we'll come back and have a look at it then. And I'll draw a schematic up, like I said too, so everyone can fully understand what's going on. Alright, I'll be back soon. I've got another little engineering sort of decision to make, and I just wanted to point it out. I haven't added the Zener yet, which will basically be in place of this black wire, to cut a long story short. And the other one will go basically from the positive output to, say, a spot in the board here. And then the other end of the pot will go to that end of the Zener. And then a resistor will go from there to the negative. I'll talk more about that later. That sets the high voltage limit, how high you can turn it up. The Zener that will be in this path will be as a reference. Now, I am thinking, for 2 reasons, to get more current, more voltage headroom so I can get more current at a higher voltage. I'm thinking about removing one of the Darlingtons, so it's a triple Darlington. But to make that work, this transistor will have to sink more current, and this resistor value will have to be decreased. The other advantage of doing that is the Zener diode will then see more current, and it'll be it'll be doing a better job of regulating. It'll also have more noise on it because of the increased current flow to the Zener noise. See, there's all these little design considerations when you're designing electronic circuits, even something as simple as this. That's why I enjoy it so much. I just want to talk about these things. Like I said, this video series is about engineering, the design of a circuit. So that's the thing. We're going to talk about all the little intricacies as we go along, and I'm going to explain all these things to you. For example, something I haven't explained yet, I'm sure everyone knows what the resistor there is for that feeds this capacitor. That's just a two-stage filter off of, the first capacitor, and that's just a dropper resistor, right? This capacitor here is a compensation capacitor. This basically decouples noise that's on the base of this transistor. Now, this resistor and this resistor here, those are also base resistors like on the transistors in the back, but they're not there for current sharing, they're there for damping oscillations. The base to emitter resistors that are here, and in the back of there, they help transistors turn off quicker. The first transistor that goes back to the comparator doesn't need a base to emitter resistor. The reason for that is because its base is constantly tied to a point that can never be zero. It's always got current flowing on it, so it doesn't need a base to emitter resistor so it can turn off. But I mean, to be honest, in a design like this, it's not strictly necessary really for even that one and the ones in the back, but it does help again with stability and stuff like that, and it does help with response timing, and there are advantages of it still. So I mean, resistors are cheap, right? There's also another little network that we have to include that's basically a resistor and a capacitor. It goes from the base of the comparator transistor back over to the output, the positive of the output. And that's basically an AC feedback path to help get rid of noise. I think it goes back to the comparator. It might go, yeah, no, it goes back to the comparator, of course. It's got to be inverted. Yeah, all right. So I just wanted to point that out because, as I just mentioned before, I'm trying to work out how much current I can get out of it at the moment for a given voltage. So I've got some design considerations to make, and I just wanted to talk about those design considerations. Something I just realized when I was talking about the base resistors, not the base to emitter resistors, the ones that are there for damping, is that the base resistor for this driver, I put a 1K in there. I meant to put 100 ohms in there. I don't know what I was thinking. 1K is way too high for that. It goes there. So, like I said, this is why I'm going to draw the schematic at the end, because if I was to do it at the start, any errors I make and any components that end up needing to be adjusted in value or type, you would all have the wrong values. But that's 100 ohms in there now. That will actually make the regulation a bit better too. Not a lot, but a little bit. I'll just turn my load back on, see what we've got. Still got no Zenas in here. We're just purely a single comparator transistor with feedback and no references. Alright. Alright, we're at 1 amp. Oh, that's looking a lot better. That's only what, 300 millivolts, I think. I'm going to go up to 2 amps. That's still not too bad for what it is, considering there's no references in it. And lossy wiring and breadboard everywhere. Okay. Don't know why I put a 1K resistor in there. Actually, let's have a quick squeeze at the volt drop across the 100 ohm resistor. That's alright. That's roughly what I want to see. How much does that increase? I could go a bit smaller. I'm just thinking. I don't want to sacrifice too much damping. What have I got on this one? Shouldn't really see anything, maybe a millivolt or two when it's doing something. There's a millivolt there. So 1 millivolt in there. That's good. I think what I might do is change that 100 ohm for... I'm just going to pause and have a think. Alright, I've decided. I was going to go like 47 ohms or 22 ohms, something like that, 27, 33. I've decided to go with 10. Although this is still a fairly low voltage circuit, the output transistors don't have much gain, so this transistor has to supply a bit of current, hence its base is pulling a bit of current. So even a 10 ohm resistor should actually be quite sufficient to still have a damping effect, and that'll be evident that it's doing its job because we'll still be able to see a small voltage drop on it that will change with load. That looks a lot better. Yeah, I'm happy with that. That's great. Alright, let's see what we can push the output to now. I've got a 2 amp load, we're still at 18 volts. Alright, cool. Okay, so just out of curiosity, we can actually get 18 volts out of it at 2 amps. That's cool, because I was thinking I was only going to get 1 amp. I can tell you now, without all the lossy wires, connections, and a reference in there, we'll be able to get 18 volts. Like I said, I might also remove a transistor and add more current there. Maybe change that transistor to, not sure. Depends on how much power I got to dissipate. And that will give us more voltage headroom too. So we'll have no trouble getting 2 amps at 18 volts. At 16 volts, we should be somewhere around 3 or 4 amps, I'd say. I mean, we can get a pretty good idea of that already. It's a good idea for me to do this sort of thing on camera anyway, because people who are learning get a good idea. I've set this to 4 amps. Let's see how it takes that. Okay, well that's just over half a volt, 3/4 of a volt. I'll go back down to 3 amps because that's what I originally thought. Yeah, with references and better wiring, that'll be doable. Okay. Let's see, down around, say, 12. I'd expect better regulation. I'll still leave some headroom because I don't have any references and we've got piss poor connections and wiring. I'm going to put 5 amps on it. That's great. Cool. Alright, so we'll be able to get 6 amps out of it at 12 volts. No trouble with the PCB, tight wiring, you know, the rest of the circuit finished, all that sort of jazz. We'll get there. So that's good news. Oh, 10 ohm resistor. Before I got the load bank, I was using a 10 ohm resistor, and then I needed to load it some more, so I got the load bank. Anyway, we're looking good. Alright, well, I've got to work out, I just realised something. When I was saying 4 VBE drops, it's actually 5 because of the comparator transistor, the way it's hooked up. So it's 5 VBE drops. So I'm definitely going to try and eliminate one of those. If it hurts regulation too much, I will put it back. If it doesn't, and I can actually get the same or better regulation with the Xena and having more current to it, yeah. So this is the thing with designing something even as simple as a 2 transistor. I know it's got more than 2 transistors, but the circuit is essentially a 2 transistor because every transistor from that transistor to the output transistor is essentially the same transistor. They're just Darlingtoned up. So it's a 2 transistor Xena regulator. It's a very simple circuit, but yet there is still stuff to consider, especially when you're building a power supply out of it, because noise, ripple, response, feedback, AC feedback response, DC feedback response, regulation, line regulation, load regulation. You got a lot of different things to think about still. So anyway, I'm gonna have a little think and see what I can do. Like I said, about knocking off one stage here, and I'll come back and report my findings. Alright, so we've got some design considerations here. I'm going to do a couple of tests actually. I'm going to power my load bank up quickly. Should have already had that on, my apologies. I could put a bigger transistor here, give it more current, and it'll do the job. And then I can bypass this. Incidentally, the way it is, and I'll just prove this. That's turned up to full voltage. If I just take this transistor out and move this link over one, bypassing it, feeding the base drive into, so it's only triple Darlington, we won't get enough output. If I wanted enough output, I would need a resistor about, let's see, too much for the transistor to handle, so I would need to put a bigger transistor there. Now, what I thought I'd do before I do that, let's just move this back. I should put that up there. Like so. Just so I've got a free row of pins for anything I need to add there, like a capacitor or something. Anyway, let's just put the load bank on 6 amps and turn it on. Let's set this. I need to change this pot. I'm using a logarithmic pot. I always get confused between A and B. One's log, one's linear. We'll set this to around 12 volts. Alright, and we'll put 6 amps on it. Is it 6? Yes. Alright, so that's half a volt. Let's put a Zener in. I know I've only got a couple of milliamps here at the most. The most current I could possibly have when I try and turn it down all the way, as low as it goes, to 0.6 of a volt, would be 10 milliamps, 11 milliamps, around that ballpark. But when it's turned up, there will not be that much at all. We'll be getting into microamps. So I'm not sure that this is going to actually work. Again, this is why I'm doing all this on camera, because I wanted to show the engineering of something. See, everyone these days just goes online, gets a bloody schematic and copies something. No one designs anymore, and this is something that really gets me going. I don't know why, I just feel like everyone's just getting stupid. No offense, but people are just not using their brain as much anymore and thinking about stuff and doing it themselves. They're relying on someone else to do the heavy lifting for them, and they just want to do the easy part and put it together. But someone else can design it, you know what I mean? I don't do any of that, you know. You can have a look at my schematic when we finish designing this and go and look on the internet. You won't find it anywhere, because this is a custom transformer, a custom heatsink with transistors already on it. I know I put different ones on it, but I am building a custom circuit to this box. So it's, you know, and I'm not just going to go on the internet and get a schematic. Yeah, I could possibly do that and have it done in a quarter of the time, but there's no fun in that for me. I'm not designing, I'm not thinking about stuff, and I get to play around watching waveforms and compensating stuff and calculating gain and current and stuff like that, you know? That's the beauty of design. If you like it, that is. I do. So we've got the Zener in there. Let's see what we get. Is that working? Oh yeah, I can only turn it down to 5.6. Okay, the Zener's working. Actually, that Zener is regulating down the bottom end. Good. So it's got enough current, but the top end is what I'm worried about. I reckon it's not going to help us here. Well, okay, it's helped a bit. What, we're dropping 70, 80, 90, 100, 110. We might have gained 10 millivolts of error. Okay. What do I need to do? I'm going to pause the video. I'm going to try a couple of things. Let me just get a data sheet for another transistor I have. Let's pause the video whilst I grab it. Alright, let's try something. I've got a 2N3053 here, trying to keep with the old school design, and a 10k resistor. That's less than half of this 22k resistor. That will give a maximum of about 24 milliamps. So yeah, 24 milliamps. Now, the thing is, when it's turned up and the comparator's not trying to pull the output down much, that's when there's not much current on the Zener. Because the thing is, with the comparator transistor, when it's trying to pull the output down, the comparator transistor is turned on. And when it's on, it passes current to its emitter, which means there's more current on the Zener. So that's the problem with this style of Zener regulator circuit, is as you turn the voltage up, there's less Zener regulation. That's good. Oh, I just wanted to point out, I changed the 550 for, oh my god, it's a 547, isn't it? What did I end up using? Yeah, 547. I just decided this project's just, it's too much of a simple project to warrant putting even half decent parts in it, especially decent parts that have gone obsolete. You know, like, that's just a bit of a waste, in my opinion. So the pin out for this, make it confusing for me. Pin 1 emitter, pin 2 base, pin 3 collector. You gotta be shitting me, I can just do this and turn it around. Neato. Now, anyone using one of these, be careful, because the metal can is bonded to probably the collector. So you want to move your components back so they don't short onto the can. Let's see if I've got this in the right way first. Yep, we've got it in the right way. Let's see how much better our Zener regulation is. Okay, there we go. That's a good improvement. Let's see if that can drive, if that's enough current to drive the output without the extra Darlington. Probably won't, but let's give it a shot. Yeah, no. Okay. But we do have better regulation. So I think what I'm going to do for this circuit, I'm going to stay with the quad Darlington. That's just the layout we're going to use for driving it, or NPN quad Darlington. Well, that's with 6 amps on it, by the way. Let's do that from where it's sensing the negative. Okay, this wire is way too thin. That's what that is. That's why I've been loading it at this end of the thick wire. If this was, like I said, on a PCB, there'll be better regulation than what you see here. One thing to remember, when you're prototyping stuff, this is just mocking it up, getting the circuit to work. Once you've been doing this long enough, you can tell if a circuit's gonna behave really, really well once it's on PCB, just from seeing it on breadboard. It's kind of hard to explain. You get used to all the little nuances of breadboards, and then you can tell how much of that is what's affecting your circuit, and work out how good your circuit actually is if you kind of deduct that, if that makes sense. Alright, sorry about that. One of my mates came to the front door and yelled out, and I had to tell him I'm busy. Alright, so what I'm thinking, let's turn this all the way down. I want to see how warm this can gets. It should only have a maximum of about half a watt going through it at the moment. Probably a bit less than that with other drops, like the drop across the Zener and resistors and stuff like that. Might be closer to quarter watt, but you know, we can probably jack up or jack down the value of this feeder resistor quite a bit. And certainly, how warm is that getting? That's still cold. Oh, did I just? No. You know, I thought I popped it when I shorted the can to the Zener then, because I saw 5.6 volts and I'm used to seeing 0.6 volts when it's turned down all the way, because yeah, I didn't think about that. No, we can lower that resistor value quite a bit more because we've got the Zener voltage drop there too now. Alright, let me turn this up so it discharges quicker through the output and the input discharge. Let's take the 10K out. Let's go with... Let me just have a look again, just so you guys know. This is what I do. Sorry, screen was locked. When I'm designing stuff, I have the data sheets up for the components that I'm using so that I can work out. You'll notice that, I'm looking at the power sections mainly, or pin outs, or power, because I'm trying to calculate stuff. And then I've got volts, watts, amps, ohms calculators, and other calculators that I have stored on my computer locally, so I don't need to be connected to the internet for all this stuff. But what was I trying to work out? You know what? Even that we won't see a quarter of a watt with the Zener diode drop. There's my problem. I've way underestimated the... let's turn off. Resistor value. Let me go grab a 2.2K resistor if there's not one here. I thought I had one here. Oh no, that was 22K. Alright, I'll be back. Alright, I've put the 2.2K in there. Powering up. Just as I suspected. Lukewarm, barely at the bottom, about a quarter of a watt. That is what we want. We should have nice regulation now. There we go. You'll be surprised how much better we can make this circuit still, but I'm trying to keep it simple, like I said. Let's see if we now have enough drive current to bypass one Darlington without losing regulation. We probably won't, but it's always worth a try, right? Let's load it. Yeah, no, not going to happen. All right, so this is, I've decided now, this is staying the quad Darlington design. Look, I could use PNP transistors and reutilize the ones that were already in there and make essentially an LDO regulator. Not that you can't do it with NPNs too, but for the main reason I've chosen to do it with NPNs in a Darlington configuration is this is the easiest way to get incredible gain and good linearity, which is what you want in a voltage regulator. So, plus NPN technology, even though we've come a long way over the years, is still superior to PNP. There's a lot of debating over this, and even I myself, I don't mind designs that incorporate both. We'll do one of those in the future. I'll show you what I'm talking about. But anyway, that's not what we're doing with this. So again, that's what 12 was called 12.1, 11.9. Well, that's what, 200 millivolts? I'm just thinking, that's a 6 amps too, don't forget. Alright. Actually, I'm going to leave this turned on. Turn this down. Something I noticed that I've not seen documented anywhere. This is quite interesting. You see, the problem with that Xena there is it's really good for acting as a reference when you're down at the bottom end of the voltage, but as you turn up to the top end, it's less of a good reference because it's a fixed voltage and it sees less current, and those two things make it a worse thing to compare your output against. Now, I got to add a limit Xena in the feedback path. Now, the interesting thing about a limiting Xena is as you turn the voltage up and it approaches that area where you start to lose regulation, the limiting Xena starts to conduct, right? And then you have a reference in your feedback path. I'll show you what I mean, because I know not too many people know this trick, and a lot of people think that Xena only helps with the limit, but I will now prove otherwise. Alright, I've just grabbed an 18 volt Xena diode. I know I might need a 20, I can't think. I'm having a silly moment, but who cares, let's just wing it. So, with this powered down, because if you unplug this whilst it's powered up, you'll pop the comparator transistor, just so you know. A lot of these circuits, as you saw when I was building it, I could actually, truth be told, at the end of that video when I stopped it because I wanted to go do load testing, when I was fitting the pot, I popped my BC550 because I forgot it was powered up. So there you go. So yeah, just don't do that. I'm just going to put that there. This is going to get connected. Wait a minute. No, that's not right. Sorry. My bad. That's why sometimes I just shut up so I can think. Sometimes when I'm talking, I don't know, do stuff wrong. Come on, what an awkward spot. Why do I keep trying to use tweezers when I've got these and they're so much stronger? I don't know. 2 seconds with them. Right, that goes to positive, the striped end. The other end goes here to the other end of the wiper, but not back to ground, just like that. We need a limiting resistor now. Now I've got to think, do we? I'm having a silly moment. I've got a 1K resistor here, don't I? Yeah. I'm just going to stick a 1K resistor in here for now. Probably want a lower value like 560 ohm or something like that, but I might need a more powerful resistor too. Haven't done the maths on this yet, I'm just winging it on camera so people can see. Okay, well that's not working. What have I done wrong? What have I done wrong? I have to go have a look at the fucking, sorry, excuse my language, picture I've got on my computer. Of a board that I made up fairly recently. I have to pause the video for a minute to find it. I found the image in question. It's a bit blurry because it's taken off my old camera, but I can still see the Xena and the resistor going to ground and my pot, because I know what the circuit was because I built it. So I don't know what I've screwed up here. Let me just have a think about this and work out what I've done, and I'll come and report my idiotic findings. I was just thinking about something as I was fiddling around with that Xena, and I just wanted to get this on camera. There's probably only about 1/4 of a watt going through here. 547 might do the job, and even better, if it runs a little bit warm, the advantage of that is it will, how do I say this? It'll drift less with ambient temperature the warmer it is. Now we don't want it too warm. I don't want to pump current through it, obviously, but I want to see. Because I've got that Xena diode in there. I keep forgetting about that. Yeah, that's not even going to get warm, so I'll put that back away eventually. I'm not going to use that. We'll just use the 547. That'll be fine with the current that I'm running. I'm going to go back to sorting out the Xena feedback for the high voltage limit, and then I'll come back. Alright, I've solved the Xena problem. It does go where I wanted to put it with that resistor there. I just had a too high voltage Xena. I wasn't taking into consideration the 5 VB drops of the quad Darlington and the comparator. So I need a way lower than 18 volt Xena. That's a 12 volt Xena, and that allows the power supply to go up to 17.46 volts. Let's see. 13 volts Xena, 1N4743. Let me see if I've got one of those. You know what, I don't have one, but a 1N40007 should do the trick. Let's turn this off and add this in here. What I'll do is I'll put those there. And add our diode there. There we go, 18.6 volt. You can't argue with that. Although, to be honest, actually I've got to lower this resistor value. That's going to bring the voltage up a bit, because there's not much current across that Xena. That's a 1K resistor. Let me just pause the video and do some math again. This is why it's so handy having data sheets up. What I've got up at the moment, I'll show you. I've got my Xena diode table so I can pick out voltages, the data sheets for the parts I'm using, and volts, amps, watts, ohms sort of calculator thing. And that's all you need to design something like this. Actually, I just want to show something. I haven't even decreased the value of that resistor yet, it's still 1K. I've got 2 amps on the load bank at 18 volts, and you all saw how much this dropped before. Bugger all. So you see what I mean? By creating a reference at the high point and at the low point, you essentially, as you start to lose regulation because the circuit's falling away from the voltage of the lower voltage Xena, the other one starts to conduct and forms a reference. It'll make more sense when I draw it out on a schematic for you guys. But anyway, let me just do some calculations on this resistor, and once we've done that, to be quite honest with you, all we've got to do is some compensation and then make up the board. Now, because it's on breadboard and it's all crappy wiring, the best thing I can do really is get rid of these crappy wires, make it up out of jumper wire, and then we'll put the scope right on the output as close as we can get to it with a custom probe. Have a look at compensation networks, what they do to it, and then we'll make up the circuit board once we know what compensation networks we're going to want in the circuit. But we won't be able to fine tune it until the board's made up. So that's where we're going from here. Alright, what I've done, this is going to be about 27 milliamps, and it's going to be about 400.49 of a watt. So we're going to have to use 2 half-watt resistors because we don't want to run half-watt resistors at half a watt. That's actually why I buy these half-watt metal films, because I use them in, how do I say this, quarter-watt applications mainly, and a quarter-watt resistor runs hotter, so you get more temp-co issues. These have better temp-co because they heat up less for a given wattage, or they dissipate the heat better, should I say, and then the resistor runs cooler and it's better. Anyway, we're going to run about just under quarter of a watt to each resistor when it's turned all the way up to 18 volts. That will decrease when it gets turned down. See, we're trying to find a threshold here that works good. Actually can't detect any heat. It's about 300 millivolts it's dropping. Zena's just lukewarm. That drops 230 millivolts, like that. With 1K, I just want to see the difference in regulation. So about the same. Okay, I think I'll meet in the middle, and although I'm actually happy with that. That's 18 milliamps with 1K resistor. I mean, it's pretty obvious, 18 volts, 1K. So I think I might leave it at that. I think that's what I'm going to do. And that makes the circuit nice and easy, because if anyone's trying to reproduce this, it's just really bog standard values, you know. 5.1 volt Zener, an 12 volt Zener, and a 4W07 diode. Bunch of 1K resistors, a 10 ohm resistor, 4.7K ohm resistor, you know, 2.2K, a few 2.2Ks, you know, BC547s, tip 41. I think one other thing I might do, or actually we're going to have to put the scope on this next before anything else. So what I'll do is I'll pause the video and I'll get rid of these little crappy jumper wires and I'll replace them with shorter, proper pieces of jumper wire, solid core. And then we'll start taking some measurements on the scope. We just want to look at it with a light load on it and unloaded and see what our compensation networks do. Because one other thing that we still have to add is basically a resistor of about 100 ohms from the output to a capacitor back to the comparator. We need to do all this on the scope. So I think what I'll do is I'll draw up a schematic. Now I'll leave the schematic until after we've done the compensation, because there's going to be at least another 2 components added to the board. And then I'll draw the schematic so everyone can have the schematic. Patch. So yeah, I'll go and tidy. It's not about tidying, it's for electrical reasons, but I'll go wire this up better and clear up my bench, and I'll be back soon. Actually, this video is getting kind of long. I think what I might actually do is get this bit uploaded and then continue working and then upload part 3 tonight. It'll probably only be a 4 or 5 part video. I know I said 3 parts, but I've tried to go over it in detail and that's taking time, so it is what it is. But anyway, as soon as this is done, incidentally, the next projects that I am starting is one of these differential amplifiers, so that'll be an interesting one, and that's happening right after this. In what I'm doing for the next couple of weeks, because like I said, in about week 3 I want to be building amplifiers, so I'm focusing on small projects like this that don't take much of my time whilst I'm sorting out components that I've got. As you all know, I'm reorganizing my lab, and basically by the time the small projects and components are organized, that'll be about week 3, and we'll be on amplifiers. Might still be working on those low noise amplifier, differential amplifier projects. They might take some time. Might need to order parts, make boards. It could just take more engineering, who knows. But yeah, I'll get this uploaded and I'll see you all in the next video. If you like the content, please like and subscribe and comment down below. You are welcome. And yeah, I'll get on with the next video. We'll start tidying this up and adding compensation and all that and get the scope out. So stay tuned.